Number 13 is another partial fraction decomposition problem from section 8.6. This time, though, we're going to have to use long division before we do the partial fraction decomposition part. The rule is that the degree of the numerator must always be less than the denominator before you can use the method of partial fractions. So I went ahead and divide the x cubed minus 9 into that pretty massive numerator there. And when I divide the x cubed into 3x to the fifth, of course, it went 3x squared times. That 3x squared then distributes to each of these terms, and I get 3x to the fifth minus 27x cubed. Please remember, whenever you use long division, you're going to subtract these out. That's why the 3x to the fifths cancel. But also here, the 27x cubes are going to cancel because negative 27x cubed minus a negative 27x cubed cancels out. So then I just have the 6x to the fourth minus 162x minus 54 brought down. Then I say, well, let's divide x cubed into 6x to the fourth. That's going to go 6x times. Then I distribute the 6x times both of those terms. When I do, I'll get 6x to the fourth minus 54x to the second. So now when I subtract those terms out, again, the goal each time is to cancel out the leading term, and it does. I'll have 6x to the fourth gone, but then I'll have positive 54x squared minus 162x minus 54 left over. So I know that the original problem, and it's good to always call the original integral of the problem I. This original integral I is equal to the part that divided out into the numerator, the 3x squared plus 6x with respect to x, plus the remainder still divided by the original denominator. Well, now that I know I'm doing partial fraction decomposition, I went ahead and factored that original denominator. We know that you could factor an x out, and when you do, you'd have x squared minus 9 left over, which factors to x plus 3x minus 3. That leads for a pretty straightforward partial fraction decomposition where I say, let's take that part inside the integral and rewrite it as some constant a over the factor x plus some constant b over the factor x plus 3 plus some constant c over the factor x minus 3. Now I need to solve for those three constants in each of these partial fractions. In order to do that, you just multiply by the least common denominator. So I'm multiplying both sides by x and x plus 3 and x minus 3 here. When I do that, that's why the left-hand side is just the numerator. I'll have a times x plus 3x minus 3, b times x and x minus 3, and c times x and x minus x and x plus 3, I should say. In order to solve for a, I already knew that all I had to do was let x equal 0 in this expression. So that's what I've done in the next step. If I let x equal 0, I should be able to solve for a. Well, when you let x equal 0 on the left, you're just going to get the negative 54. The x terms cancel out. On the right-hand side, notice the b times 0 and c times 0 would cancel out. You're going to have a times 3 times negative 3, so I get negative 9a is negative 54. When you divide by negative 9 on each side, you'll get a is positive 6. Okay, now I have my answer for a. In order to get to my answer for b, I would want to let x equal negative 3, and I should be able to solve for b. That's what I've done here. So if I let x equal negative 3 on the left-hand side, it becomes 54 times negative 3 minus 162 times negative 3 minus 54. Now that's what I've done here. When I entered that into my calculator, I got 918. Surprised me it was such a large number. On the right-hand side, I would have b times negative 3 times a negative 6. Well, negative 3 times negative 6 is a positive 18b. I get positive 18b is equal to 918. B is going to equal 51. Now for C, I know I could solve for c by letting its denominator equal 0. That's going to happen when x is 3. So I come down here and let x equal 3. On the left-hand side, when you plug in the 3, you're just going to be left with a negative 54. On the right, you'll have c times 3 times 6. Well, 6 times 3 is 18. 18c is 54. Divide by 18 on each side, you'll get c equals negative 3. Okay, so now I have my a, b, and c solved out. I'll go ahead and rewrite the original integral. This original integral, which was this, is now, well, it's the integral of everything I had there. That's super easy to integrate, plus these three partial fractions. So I said plus 6 over dx over x plus 51 on the integral of dx over x plus 3, and then minus 3 times the integral of dx over x minus 3. Each of these integrals now are super easy because every time the derivative of the denominator is in the numerator, we know it's just the natural log of the absolute value of the denominator. So then we can use the power rule on the first two. The last three are all logs. So we can just say, well, this is going to be x cubed plus 3x squared plus 6 natural log of x plus 51 natural log of x plus 3, and then minus 3 natural log of x minus 3 plus that constant of integration. Final answer there. And please do keep in mind that inside these absolute values, it's going to, inside the natural logs, you are going to have to use absolute values around the terms. No reason to condense or anything in this problem. You could condense the 3 logs to one log function. You can do that. There's just no need to. The next problem. This is, again, from 8.6. And in 8.6, it was wanting us to know the best technique to use. The best technique to use anytime you have an inverse trig function, well, it's a no-brainer. It has to be integration by parts. In your integration by parts, the mnemonic that we use to know what to let u equal is Liate. The second letter in Liate is I, stands for inverse trig functions. So the only thing that would be more obvious that it's an integration by parts is if you had a logarithm in there. We don't have that, but we do have the inverse trig. So I'll say, well, all right, so u is going to be the inverse trig function, which is the inverse sine of 3x. That means the only other term in there is dx. I have to let that equal dv. Now keep in mind that's understood to be a 1 dx. So if you integrate 1 with respect to x, you know v is x. The derivative of your inverse sine formula, which you do have to have memorized, is 1 over the square root of what's inside squared. And then the chain rule says times the derivative of what's inside. Well, that's where the times 3 is coming from there. Now, and again, of course, that's the derivative with respect to x. When I try to simplify this, my integration by parts formula is u times v. So u times v, that's going to give me x inverse sine of 3x. That's where that came from. And then it would be minus the integral of v du. Well, minus the integral of v du, this x is going to go up in the numerator here. I'll go ahead and factor that 3 out front. And that's what I've done. I said u times v minus the integral, factor the 3 out front, and I had x over the square root of 1 minus 9x squared dx. Then at that point, I could see that this integral that I had in red wasn't able to be integrated with our basic rules. So now I just use the substitution rule to help evaluate it. I said, let's let t equal what's inside this parentheses, the 1 minus 9x squared. dt is going to be negative 18x with respect to x. I can already see I had the x dx in there, but I needed the factor of negative 18. Well, I multiplied by negative 18 on the inside, divided by negative 18 on the outside. Now this is going to be easily integrable with our basic rules. We've already integrated the u times v. This coefficient out front minus 3 over minus 18 gave me plus 1/6. And on the inside, now every bit of this is going to become du. So then I'm just left with 1 over the square root of t. I should have said that's going to become dt. Every bit of that becomes dt. Then I'm going to have 1 over the square root of t dt. So that's just the same thing as t to the negative 1/2 power. Now I know that the integral of t to the negative 1/2 power is going to be t to the positive 1/2 power divided by 1/2, which means multiplied by 2. Of course, I still had my 1/6 out in front. That 2 times 1/6 is going to give me 1/3. And I would have 1/3 times the square root of t, where t is this group right here. I went ahead and thought it looked better to write that as the square root of 1 minus 9x squared all over 3. And then, of course, remembering to bring down the first term as well, the x inverse sine of 3x plus that square root over 3 plus the constant of integration. It's a good problem. Like that one a lot. Number 15. Number 15 is a problem in which you might have been able to get away with not using proper form on MyLab because it's hard for them to force you to do that since they can't grade your handwriting and stuff. Please do keep in mind in this problem, I will give you an integral in improper form. And for me to give you credit for it, you must put the integral in proper form. So whenever you're looking at this, you're like, well, what do you mean he's giving me an integral in improper form? One of the limits of integration is going to be impossible. So when you look at this, you say, oh, it's because when I try to plug a 7 into that, I'm dividing by 0. The function on the inside does not exist at the left-hand or at the lower limit of evaluation. So I have to say, well, I need to take the limit as a approaches that number. And anytime it's a lower limit, you can only approach that number from the right. It has to be a one-sided limit. So what if you didn't do that? What if you just had that? That's wrong, because then you could say, well, are you approaching 7 from the left? No, you're not, because every value in this interval from 7 to 19, so we're starting at 7, we're ending at 19, every value in this integral is approaching 7 from the right. Now, if this denominator had been the cube root of x minus 19 and the upper limit would have been undefined, then I would have had to approach that upper limit from the left-hand side. So anytime you replace the lower limit, you're going to have to approach it from the right. Anytime you approach or have to replace the upper limit, you're going to have to replace it from the left. So please do keep that in mind. So the one-sided limit as a approaches 7 from the right of the integral a to 19. And I went ahead and put the inside part in a manner that makes it easier to integrate. That's the same thing as x minus 7 to the negative 2/3 power with respect to x. So then I can just integrate that with my power rule. I can say, well, x minus 7 to the negative 2/3 is going to become x minus 7 to the positive 1/3 divided by 1/3, which means times 3. So integrated on the inside. And please do keep in mind, you have to keep that limit in every step until you can physically plug an a in for x and a 7 in for a. So you say, okay, I'll have the limit as a approaches 7 from the right of this integral 3 on the cube root of x minus 7 evaluated from a to 19. When I evaluate at the upper limit, I can just say, well, I can plug a 19 into that, and it'll be 3 on the cube root of 19 minus 7. That's going to be 3 on the cube root of 12. Now, notice from this step to this step, I did not put the limit. Well, why? Because I physically plugged a 7 into the place for the variable in this problem. So I can say, well, that's just going to become 3 on the cube root of 7 minus 7, whereas it was undefined in the original problem. Now when we integrate it, it's not undefined. It's just the cube root of 0, which is 0. We'll get 3 on the cube root of 12 minus 0 for a final answer of 3 on the cube root of 12. The integration in these problems and the evaluation on problems like this should not be hard, but I will be really looking to make sure that you're doing this change an improper integral to a proper integral part for this one. That's the main thing I'm looking for on this problem 15. For problem 16, we're starting chapter 10 where we look at sequences and series. It looks like 16 and 17 are sequences, which then means the rest of the problems are all series. With a sequence, you're going to have a general formula that represents the terms of the infinite series. So we have the general formula here, a sub n is equal to 6 to the n minus 4, starting at n equals 1. Find the first four terms and state why the sequence either converges or diverges. So this was pretty straightforward. And I said, well, okay, when n is 1, you're going to have 6 to and this a sub n, I don't know why I put 6 to the fourth over there. It's 6 to the n. So 6 to the n minus 4, as you can see above. When I plug a 1 into it, you just get 6 minus 4. That's where the 2 came from. When you plug a 2 into it, you get 6 squared. 36 minus 4 is 32. When you plug a 3 in, you'd get 6 to the third, which is 216 minus 4, 212. And then when you plug a 4 into it, which I guess is what I had that up there, 6 to the fourth power, 1296 minus 4 is your 1292. And of course, this continues on and on and on forever. As it continues on and on forever, we can easily see that this is not going to approach any one number. It's going to diverge off towards infinity. So I can say this sequence diverges because the limit as n approaches infinity of the general term a sub n is clearly infinity. It's going to get large super quick. The next problem gives us a equation for the general term a sub n is n over the square root of 25n squared plus 8. And it says if the sequence converges, state its limit, otherwise state it diverges. And again, for sequences, the rule is if the limit as n approaches infinity of a sub n is any one number, it converges to that number. Otherwise, it diverges. So in this case, I can just say, well, all right, this is going to be fairly straightforward. When I'm thinking about that denominator, anytime you have a limit as n approaches infinity, you only have to worry about the fraction of the leading coefficient. So when I'm looking at this problem, I didn't write it, but I thought of it as this. The limit as n approaches infinity, my numerator has an n, the square root of 25 n squared in that denominator, that's the same thing as 5n. And then, yes, there's more to it, but it doesn't matter. The only thing that matters is the fraction of the leading coefficients. And in that case, it's going to be 1 over the square root of 25, which is going off towards 1/5. Since the limit as n approaches infinity of the general term a sub n is equal to 1/5, we say, well, the sequence converges to 1/5. Now, had this been a series, it would diverge by the test for divergence, because the test for divergence says that if the limit as a sub n doesn't go to 0, then the series diverges. But that's the difference in a sequence and a series. A sequence, you just have to show that the limit goes to any one value, and if it does, it converges to that value. Now, speaking of series, the rest of the problems on the test will all be series problems. Start off with a geometric series where you can say, okay, after the first term, every term thereafter is going to have some common ratio r that I'm multiplying each one by. So this series was the summation from 2 to infinity of 7, as n approaches 2 to infinity of 7e to the negative n. So I can say, well, that's the summation from 2 to infinity. All I've done is I tried to write it more like a geometric series where I could see what the r value is. I know that if e is raised to the negative n, then 1 over e is raised to the positive n. That's what I've done right here. This makes it more obvious that okay, each term after the very first term is going to be multiplied by an increasing power of 1 over n. Well, okay. Now, the first term of a geometric series is what we call C. C is just the first term. Well, the first term in this series starts at 2. So that's why I've plugged this in right here. My first term is going to be 7 times 1 plus e quantity squared. And that's going to give me 7 over e squared. That's the first term of this series. Every term thereafter continuously gets multiplied by an additional factor of 1/3. The next term would be 7 times 1 over e cubed. The next term would be plus 7 over 1 over e to the 4th, and so forth. So since that absolute value of r is equal to 1 over e, the rule for a geometric series is anytime the common ratio, the absolute value of the common ratio is strictly less than 1, the series converges. That just means that the terms are getting smaller. So in this case, each term's getting multiplied by almost 1/3. Clearly, they're getting smaller. My series is going to converge. What does it converge to? Please remember your convergence formula is C over 1 minus R. C is just your first term, that's brought down here, divided by 1 minus R, 1 minus 1 over E. I wanted to go ahead and get rid of the fractions in this, so I multiplied the numerator and denominator by e squared. That gave me a 7 in the numerator. When I distributed the e squared into the denominator, it would give me e squared minus e. And then this would be my exact answer, 7 over e squared minus e. If you wanted a decimal, you could go to your calculator, and it would tell you that that is approximately 1.499. Now, the test for divergence, and please keep in mind with the test for divergence, it can only ever tell you if a series diverges. It's either going to say, hey, the series diverges, or it's inconclusive. That's the only two options. So in this one, it says use the test for divergence to determine if the series 5k over 3 plus 2k squared, starting at k equals 0 to infinity, diverges, or if the test is inconclusive. All right, so the rule is that the limit, as in this case k approaches infinity, of the general term 5k over 3 plus 2k squared, if that's not equal to 0, we say it diverges. In this case, it would, because you'd say, well, your numerator is lower degree than your denominator, so your denominator is infinitely times larger than your numerator. This fraction is going to go off towards 0 as k goes to infinity. So because it goes off towards 0, we just say that the divergence test is inconclusive. This series could converge or diverge. Now, later on, if I ask you to use a p-series and comparison test, you'd say, hey, this is a multiple of a p-series, p equals 1. What do I know about that? They always diverge. They're called the harmonic series. It is a divergent p-series. But that's not what's asked in this question. This question is just the test for divergence, and the test for divergence would be inconclusive here. So we could say, by the divergence test, this series could converge or diverge. Now, I ask us to use the comparison test or the limit comparison test on this next one to determine the convergence of the series from n equals 1 to infinity of n plus 5 over n cubed minus 8n plus 7. Now, what you're supposed to be thinking about here is that, well, what type of p-series, and I know this is a p-series, anytime your numerator and denominator are polynomials, this is a rational function on the inside of that for the general term. You always want to compare it against what's the degree difference in the numerator and denominator. Well, the numerator is understood to be degree 1, denominator is degree 3. I would want to compare this with a p-series with p equals 2. Now, that's what I've done here. I've said I'm going to use the limit comparison test with the p-series 1 over n squared. And I know that 1 over n squared is a convergent p-series. The rule for convergent p-series is that the degree in the numerator and denominator has to be greater than 1. If it's less than or equal to 1, it diverges. This is 2, so my denominator gets large enough, fast enough to make this series converge. So I can say, okay, how am I going to prove something with a p-series in a limit comparison test? Well, since this converges, all I want to show is that the series in question here is just a constant multiple of this convergent series. And then a constant multiple of something that converges also converges. That's the logic of the limit comparison test. So I'll say, okay, let's let L equal the limit as n approaches infinity of the general term of the series I'm trying to prove something about divided by the general term of the series I already know something about. And when I do that, I can say, well, okay, that's going to give me the limit as n approaches infinity. Here's the series in question. If you're dividing by a fraction, you're multiplying by that fraction's reciprocal. So I say times n squared over 1. Now, the nice thing about that n squared, of course, would go through and it would distribute into this numerator. This is going to become the limit as n approaches infinity. And here's, again, where you're using the concept of a limit going to infinity. The only terms of relevance are the largest powers in the numerator and the largest powers in the denominator. Anything else is infinitely times smaller. So I could care less about that 8n term there. I could care less about that 7. I could care less about that 5. They're infinitely times smaller than the leading coefficients. So I can say, well, this numerator is the same thing as n cubed plus, yes, there's going to be some other terms. I do ... just show those other terms do not matter. My denominator is going to have an n cubed plus some other terms that don't matter. The limit as n approaches infinity of n cubed over n cubed is going to go to 1. What this is showing us is that the size of the series in question, it's almost identical to the size of the series that we know converges by the p-series test, since it has a p-value of 2. So I can say, since L is equal to 1 and the series I'm comparing it to converges, then the series that we're interested in also converges. Limit comparison test with a p-series, p equals 2. Next up, alternating series. Alternating series, obviously, when we have an alternating sign, that's going to make it go from positive to negative. Alternating series test, it looks a lot like the divergence test. What you're going to do is take the limit as n, or if the index would be k, you'd say k approaches infinity. In this case, it's n. So the limit as n approaches infinity of the non-alternating part. Well, the non-alternating part of this is this general term right here. So I can say, well, the limit as n approaches infinity of n over the square root of n cubed plus 5. When I'm thinking about this, I'd say, well, this is equal to the limit as n approaches infinity of n over the first term in the denominator would be n to the 3 over 2. And then any other term wouldn't matter. What do I do with this? Any time you have a limit going to infinity, if the denominator's degree is greater than the numerator's degree, we know it goes off towards 0. So I can say, well, the limit as n approaches infinity of this fraction is 0. Therefore, this series converges by the alternating series test. Now, what if it had been anything other than 0? It would diverge by the alternating series test, or you could even say it diverges by the test for divergence. Either way would work. But in this problem, I specifically said use the alternating series test, so that's what I've done here. So since this is 0, the series converges by the alternating series test. Up next, asking us to use the ratio test to determine if this series n factorial quantity squared over 6 times 2n group factorial converges. I forgot to put the converges on there. So use the ratio test to determine if that series converges. Okay, so the ratio test is asking us to look at the, in your book, it would have said the a sub kth plus first over the a sub kth term. Most books say a sub n plus 1 over a sub n. You just say, well, it's the next term over the term right before it. So if I look at the a sub n plus first term divided by the a sub nth term here, a sub n plus 1, I would go into my function here and replace every n with an n plus 1. So my numerator, instead of n factorial quantity squared, it becomes n plus 1 factorial quantity squared. My denominator is going to become 6 times 2 times n plus 1, then group factorial. So that's what I've done here. I'm multiplying that by the reciprocal of a sub n. So notice my 6 times 2n factorial goes in my numerator. My n factorial quantity squared goes in my denominator. Now in the next step, here's where I was just trying to make some sense out of this. I know that n plus 1 factorial quantity squared and this n factorial are going to have a lot in common, so I grouped them together. And I said, I know that n plus 1 factorial squared, that's going to have an n plus 1 times an n plus 1, which is going to be n plus 1 squared, and then times the other terms, one integer value less than that, which is going to be n factorial. Well, those are going to be squared as well. But those can cancel with that n factorial in the denominator, leaving me only that very last term times itself because of the squared as the term remaining in the numerator. So I have a numerator of n plus 1 quantity squared for that part. Now, the other term in the numerator is the 6 times 2n factorial. So I can say, well, this right here, this would be 2n plus 2 factorial. 2n plus 2 factorial is going to be 2n plus 2 times 2n plus 1 times 2n factorial. That's what I've tried to show over here. So this denominator is going to be 2n plus 2 factorial, which is 2n plus 2 times 2n plus 1 times the 2n factorial. That 2n factorial canceled with the numerator. Of course, the factor of 6 also canceled with the numerator. Now, that's leaving me, L is going to equal the limit as n approaches infinity of the a sub n plus first term over the a sub nth term. This is going to equal the limit as n approaches infinity of the only term left in the numerator is n plus 1 squared. The terms I have left in the denominator are going to be the 2n plus 2 times 2n plus 1. So I know that this limit as n approaches infinity is going to simplify out to be the leading term in the numerator is going to have an n to the second, plus the rest of the terms don't matter. Similarly, in the denominator, I would have a 4n squared plus a bunch of other terms that don't matter. So then when I take the limit as n approaches infinity, I'll just get my 1 over 4 for 1/4. Now, what the ratio test says is that if this limit as n approaches infinity, the a sub n plus first term over the a sub nth term, anytime that's less than 1, that's evidence that your series converges. If it's greater than 1, it diverges, and if it's equal to 1, your ratio test is inconclusive. In this case, it's definitely conclusive. I can say since the L limiting value was 1/4 and that's less than 1, this series converges. Final answer. Number 23. We have it says determine whether the summation from k equals 1 to infinity of 4 plus 7, the cosine of 7k over k to the fourth converges, and then justify your answer. All right. I tried to make this one pretty obvious here because notice minus that cosine here, this would just be a p-series with p equals 4. And anytime in a p-series, if the value is greater than 1, it is convergent. Something, okay, this is definitely going to converge, but I have to explain why. So I'm going to explain why with the comparison test. I can say, okay, comparison test. What do I know? I know that this numerator, the cosine of 7k, at most could be 1. So it could be less than or equal to 1. So I can say, well, then this numerator here, 4 plus 7 cosine k, would be less than or equal to 5. And then, of course, then this fraction would be less than or equal to 5 over k to the fourth. Now, I can say since the summation of 5 over k to the fourth is a multiple of a p-series, this 5 could be brought outside, and technically you could say it's 5 times the summation of 1 over k to the fourth, which would make that a p-series with p equals 4, which is a convergent p-series. 5 times a convergent p-series is still a convergent p-series. So I can say, since this is a multiple of a convergent p-series with p equals 4, and the general term of the series in question is less than the general term of a series that we already know converges, then the series in question must also converge. All you have to do is show the general term of the series of interest is less than the general term of a series you know converges. That's all the evidence you need to show that your series converges. Last problem, I believe. Yeah. So in 24 here, I'm asking you to find the interval of convergence. And again, these problems, you always find the interval of convergence using the ratio test. So problem 22 and problem 24 might as well just say use the ratio test. You find the interval of convergence using the ratio test. So you'll notice that's what I started out doing. I said, I'm going to have to think about what the absolute value of the a sub n plus first term over the a sub nth term is. And again, your book would have used a sub k plus 1 over a sub k. Doesn't matter. The choice of indices is totally arbitrary, but most choose n. So I'll say, okay, in my numerator here, a sub n plus 1 is going to be 5x minus 4 to the n plus 1 power. That's where this came from. Divided by your denominator is going to be n plus 1 cubed plus 5. That's where that came from. So all of this is your a sub n plus 1. I'm multiplying that by the reciprocal of a sub n. So that means the 5x minus 4 to the n goes in the denominator, the n cubed plus 5 goes in the numerator. Now in the next portion, I'm collecting like terms. I just said, well, I know this 5x minus 4 to the n is going to cancel with all but one of the powers of this 5x minus 4 to the n plus 1 up here. So I'm going to have a 5x minus 4 as a factor, and then that factor is going to be multiplying n cubed plus 5 divided by this n plus 1 cubed plus 5. Okay, so then the ratio test is going to say that my limiting value L is the limit of this general term a sub n plus 1 over a sub n. And this problem I've already shown that that's the limit as n approaches infinity of 5x minus 4 times this fraction. Well, this fraction, since I have a limit as n approaches infinity, the only thing I need is the highest degree in the numerator and the highest degree in the denominator. It's going to be n cubed plus a bunch of terms over n cubed plus a bunch of terms. Those terms are irrelevant. I only need the fraction of the leading coefficients, which is 1 over 1. So you said, well, when I take the limit as n approaches infinity, this just becomes the absolute value of this group. This group didn't have an n, so it stays. It's multiplied by 1. I'll just get the absolute value of 5x minus 4. Now, the ratio test tells us that our series converges if the absolute value of a sub n plus 1 over a sub n is less than 1. So how is the absolute value of 5x minus 4 less than 1? Well, it's less than 1 if 5x minus 4 is less than 1 or greater than negative 1. So I had to set up a 3-part inequality. I'll add 4 to each portion, and I'll get 5x is between 3 and 5. Then we divide by 5, and x is going to be strictly greater than 3/5 or strictly less than 1. Now, I said strictly greater and strictly less. We actually don't know that for sure. This is the only thing that the ratio test guarantees. If x were to equal 1, then this equation up here would equal 1. And if x were to equal 3/5, this equation up here would equal 1. Well, the ratio test is inconclusive at those values, so you always have to test your endpoints. That's what I'm doing here. So I can say, okay, let's test that left-hand endpoint. The way you test it is you literally plug it into your original summation here. So I can say if I plugged x equals 3/5 into that series, or the summation of the series, I can say, well, what's going to happen is I'm going to have 5 times 3/5 minus 4 on the inside of that. Notice that's going to be 3 minus 4. 3 minus 4. 3 minus 4 is a -1. I'm going to have -1 to the n power up there. And you're plugging it in for x, nothing else happens to the n term. So you say, well, I'll have -1 to the n power over n cubed plus 5. That's an alternating series, and I can say, well, all I would have to do is take the limit as n approaches infinity of the non-alternating part, which would be 1 over n cubed plus 5. That clearly goes to 0 as n goes to infinity. So this series converges. Well, what does that mean? It means, yes, x can equal 3/5. When I try to let x equal 1, if you plugged 1 into the original function, you'd have 5 times 1 minus 4 to the n. You say, well, that's just going to be 5 minus 4. That's 1 to the n. 1 to the n is just 1. So my numerator here, you'll notice I just put a 1. There's no reason to put 1 to the n. 1 is always 1, no matter what power you raise it to. So I have 1 over n cubed plus 5. What I know about that, the p-series difference in the numerator and denominator is 3. So I would compare this to a p-series with p equals 3. And I know that this, term by term, it's going to be smaller than 1 over n cubed. This denominator is always larger than this denominator. So this fraction is always smaller than that fraction. If you're smaller than a convergent series, then that's evident your series also converges. So I can say, well, it converged at 3/5, it converged at 1. In this case, both the left and right hand endpoints are included in this interval of convergence. So we can say the interval of convergence is x equals bracket 3/5 to 1. Final answer. All right, guys. Hopefully that helps you study for this Calc 2 Test 2 covering sections 7.1 through 11.2. I know it's a lot of material. Let me know if you have any questions.